Okay, so last time what I did was I gave a quite unsatisfactory introduction to the theory of Fourier transforms. And what we talked about is four types of transforms, which I called FCD, FCC, FDC, and FD. Okay, and there was a pattern to how these things worked. So and the pattern had to do with whether in the time domain we were periodic or aperiodic, or continuous time or discrete time. And so for the FCD, we were continuous time in the time domain, okay, and periodic. And the periodicity led to discrete frequency domain, okay? So when we took the Fourier transform of something which was periodic and continuous time, we got something which was discrete time and aperiodic, all right? Now for the FCC, we're talking about aperiodic and continuous time, and the result was aperiodic and continuous frequency, all right? Discrete continuous, so FDC, meant discrete in the time domain, which led to periodicity in the frequency domain, okay, and aperiodic here gave rise to continuous time here. And then finally, we had the discrete Fourier transform, the DDFT, and this was discrete time and periodic, led to discrete time and periodic in, or discrete frequency and periodic in the frequency domain, okay? So this terminology here is very nice, I think, but it's not mine. It comes from this nice book on signals and systems by Quakernack and Savan. And being a nice book, it's of course no longer in print. But if you can get your hands on a copy, it's a nice treatment of signals and systems. Not quite at the mathematical level as what I'm doing here, but done by people who have some taste and style. All right. Okay, so so what I did last time was I wrote down the formulas for all of these transforms, and what we'll do now is we'll study them in detail separately. Okay, and what we're going to see is that in all of these four cases, with the exception of the last, the transform has a slightly different character depending on the kinds of signals that you give it. Okay, so in these cases, there's function spaces that you can select from to give to these transforms, and the theory of the transform differs depending on the function space that you choose. And we saw that for these three, the natural function spaces to choose were L1. So L1 per here, L1 on the real line here, and little L1 on the sampled real line for this one. Okay, so we're going to start with the CDFT. Okay, so continuous time periodic, and we're going to look at the L1 case, since that's really the most natural case in terms of the definition of the transform. Okay, so the L1 CDFT. All right, so last time I wrote down the definition for this thing. Okay, so first of all, it was a mapping from L1 per T. Okay, so L1 on each period, capital T periodic. And we decided that we were always going to talk about, for Fourier transforms, complex functions. And so what we got out as we saw last time, was a discrete frequency signal on the sampled frequency domain with sampling interval 1/t. Okay, and the formula is okay. All right, so I'm going to start out by computing a couple of transforms. All right. So maybe, sorry, before I do, maybe let me just remind you why we're using L1 here. Remember that for this definition to make sense, that the integrand here should be integrable, which meant that its absolute value should be integrable, which means because this has magnitude 1, it means that f should be absolutely integrable in the interval 0t, which exactly means this. Okay, so this is the natural space. In terms of existence of the transform, this is the natural space for the CDFT. Okay, so let me, as I was about to say, introduce some examples. And so these examples are not just to sort of illustrate grinding computations, because you can do grinding computations for Fourier transforms. All right. Rather, the examples are, I hope, meant to be illustrative of something. So I'm going to work with two kinds of examples. The first pair is going to make connections to the approximate identities that we talked about last time when we were talking about, well, I forget whether it was last time or the time before, but when we were talking about approximate identities and convolution. Okay. All right, so the first signal we will compute, well, we're not going to calculate it. I'm going to just write it down for you because I generally refuse to do integrals live in front of other human beings. Simple ones. And so these signals I'm going to think about as being defined on the interval 0t. And very often when I think about periodic signals of period t, I'll think of them as being defined on 0t, but it doesn't really matter what period you define them on. And here it's convenient to work on -t/2 to t/2. Okay. So I'm going to choose some a in 0 t/2. Okay. And the signal that I'm going to calculate or give you the CDFT for is the signal which takes the value 1 between -a and a and 0 elsewhere. Okay. And so, of course, this thing is periodically extended, and so it's going to go on out here and similarly out here. Okay. So I only draw one period, of course. Okay, so let's think about calculating the CDFT. Okay, so it's not a hard computation, but I'm still not going to do it sort of in detail because it's so easy in this case. So first, let's think about the case where n is equal to 0, because when n is equal to 0, very often in these transform computations, n equals 0 arises as a special case. And the reason is very simple. Usually you end up having to integrate a harmonic. And if you integrate the harmonic when n is not equal to 0, then you're going to get a 1/n in the denominator when you do the integral. Okay, so n equals 0 is a special case here. And so when n is equal to 0, this thing is 1. Okay, and so the CDFT at 0 is simply going to be the integral of f over its period. Again, that's always going to be the case, of course. So the CDFT of this signal f at n/t is, so it's the integral of f, which is 2a, when n is not equal to 0. And then when n is equal to 0, it's a only slightly harder computation to do. So I'm going to be just integrating. So remember, I'm going to do the integral over this period, not the period from 0 to t. Instead, I'm going to do the integral from minus t over 2 to t over 2. So I'm just integrating now the function, and because it's 0 outside the interval of minus a to a, I'm really just integrating the function 1 from minus a, I'm integrating the function e to the minus 2 pi I n t over t from minus a to a. Okay, so that's an easy thing to do, and there's just a little bit of simplification that you can do there. And upon simplifying, you get this. Oh, so this is, sorry, n not equal to 0. Here it's n 0. Okay, so we make an observation here, and that is that this is exactly equal to the sampled Dirichlet kernel that we had talked about previously. Okay, so that's an interesting little fact. Okay, and and you can see here that as you increase a, okay, so that increases a, and that increases kind of the frequency of the argument here. Okay, and so in terms of the Dirichlet kernel, this corresponds as you increase a, it corresponds to taking this behavior and focusing more and more about 0. Okay, but you can only make a so big, from namely t over 2. All right. All right, so let's just sort of store that little fact about the CDFT of that thing. And let's look at another signal that we're going to transform. And maybe we'll just call this one F as well. Since it's just, for our purposes right now, it's just some generic signal. It's going to be a similar kind of a thing in the sense that we're going to define it on the period from minus t over 2 to t over 2. Okay, so minus t over 2 to t over 2. And there's going to be some a involved. Okay, but now what we're going to do, so here I have 1, and so I'm going to go up to 1 and then down to a. Okay, so that's my signal, and of course, again, this thing is periodically extended here, like so. Okay, so this is now a slightly harder computation to do in this case, because you have to integrate some linear function of t times a harmonic, which you do by integration by parts. So when n is equal to 0, as is always the case, you're just integrating f over a period. In this case, that integral is a. Okay, and then when n is non-zero, so again, you have some integration by parts exercise to carry out here. And upon doing so, you get sine pi a n over t squared over pi squared a t over t squared. Okay. And the thing to notice here, rather similarly to what we did previously, is that this is a sampled version of something that we've seen before. This is now the sampled Faget kernel. Okay, and as we increase A, okay, the frequency here increases, and the sort of amplitude decreases, okay, as A grows. But again, you're kind of bounded by Q over 2 in terms of how big A can be. Okay. All right. Okay, so those are two examples that are going to be kind of interesting to kind of just leave lying in the background, and they're going to show up when we talk about some general Fourier type things later on. All right. So the next two examples are going to be used to illustrate certain basic things about the CDFT as we go along. Okay, so the first one I'm going to call F, and I will refer back to it in the future as F, and there's going to be a G that follows this, and then later on, when the time comes, there's also going to be an H. Okay. And F, again, I'll just draw its graph. And so F is defined on the inner, it's going to be one periodic just for concreteness. So one. And it's defined like so. So I'm going to define it on a single period from 0 to a half. It has the value 1. And then from half to 1, it has the value -1. Okay. All right. And so now this thing has to be periodic, so you have to mess around a little bit thinking about what's the value at these points of discontinuity here. Doesn't really matter what you take as long as the function is continuous. And, you know, it doesn't even really matter if it's continuous. If there's some disagreement on sets of measure 0, it doesn't matter. Okay. Point is, you don't have to fuss around with what the value of the function is at the endpoints, or sorry, at the points of discontinuity, which includes the endpoints as well as the point and a half. Right. So now let's just give the formula for the CDFT of this thing. So you know, this is just an easy calculation that I don't want to bore you with. Okay, so t is 1, so these are just evaluated at points n. And when n is equal to 0, so again, this is going to be a special case, and when n is equal to 0, it's just the integral of f, but that's 0 because the area cancellation business that goes on there. Okay, and then when n is not 0, you get this. So you do some calculation, and this is what comes out. So I think yeah, sorry, I got these backwards up here, apologies. Okay. All right. Okay, so there, that's F. Again, we're kind of just going to store this for a moment, and we're going to go back and make reference to this, you know, a little bit for trivial things later this lecture, and for slightly more interesting things a little bit later on. Okay, so now we're going to introduce another signal G, and again, G is going to pop up for us in various things we talk about with CDFTs. Okay, and G is defined thusly, so it is also going to be periodic with period 1. And what it's going to do is it's going to go from 0 to a half between 0 and a half, so it goes with slope 1, and here back down to 0 with slope -1. Okay. All right, and so there's a calculation that you have to do here again, and again, because you're going to be integrating things that are linear like this, there's going to be some integration by parts to integrate, t times a harmonic. I'm not so very interested in those kinds of details, but you can do this. Okay, so when n is equal to 0, it's the area under the curve again, which is a quarter in this case. And then when n is not equal to 0, you get minus 1 to the n minus 1 over 2 pi squared n squared. Right? Okay, so again, we'll cache that and make use of it later. Okay, good. So let's now turn, oh yeah, sorry, before I do that, let's remember from last time I said that you could use in your definitions of the Fourier transforms, you can use the complex harmonics, or you can also use sines and cosines, all right? I will always use the complex harmonics because of the reason we're about to see now. And that is, you have to use sines and cosines. So we can also use the real harmonics. So it's a cosine 2 pi n t over t, and sine 2 pi n t over t. Okay, and if you do that, then you're gonna, you have to have kind of two transforms, one for the cosines and one for sines. That's why one reason I don't like doing it. Okay, but let me write it down. Okay. So you can have C, CD, so this will be the cosine transform. And this just has the obvious definition. And you can do this for any non-negative integer, n. And then there's the sine transform. Like so, and you can do this one for any positive integer. When n is equal to 0, you get nothing. Okay. And whether you choose to do the CDFT or both of these and then combine them, it doesn't really make any material difference. There's just an obvious convenience of doing this way. Okay, but so one can combine FCD with CCD and SCD by the Euler's formulas. So e to the 2 pi I n t over t is cosine 2 pi n t over t plus I sine 2 pi t over t. So that way you can go from these ones to this one, or you can go the other way, and you would get, by using cosine, 2 n pi t t is 1/2 e to the 2 pi t over t. So plus I e to the minus 2 t over t. Okay, or and you can also back out sine from this. Okay, and so the point is you can freely go from these two to this one and back. Okay. And that is something we will never do again, but some people do it that way. All right. Okay, so let's maybe list some elementary properties of the CDFT. Okay. To do so, let's introduce some notation. Well, first let's recall some notation. First is sigma star f, which is sort of the swapped signal. So this is the signal whose value at t is f at minus t. Okay, so I flip the graph about the independent variable axis. And there's the shift operator applied to a function. So shift by a. It's defined like so. Okay, and then also I'm going to make use of a sort of modified version of the CDFT, which I'll write with a bar on top because there's a conjugation that's happening, complex conjugation, and this is defined by so. Okay, and this differs from the CDFT just by a minus sign there. Okay, so that's why the bar, because I've conjugated that. All right. Okay, so now with this notation, I have some properties, and these are very elementary, so I won't prove any of them just because they're very simple. All right. So the first says, if you take the CDFT of f, okay, and you take that function of frequency and you conjugate it, okay, take the values and apply the complex conjugate to the values, this is the same thing as doing this. Applying this alternative transform to the conjugate of the signal. Okay, that's one fact. Again, you just directly verify that that's true by plugging everything in, and, making some change of variable in the interval and stuff like that. Okay. So the CDFT of a reversed swapped flipped signal is the flip of the transpose. Okay, and it's also that. Okay, so again, that's just a direct check. Then you might wonder what's the CDFT of a shifted function. Okay, so oops, FCD of tau A star F. Gives a value of that at a certain frequency. And so, to calculate this, okay, so we're going to you make use of that. And then if you just come up to the definition here, okay, so rather than t in here, you're going to have t minus a. And so what I'm going to do is I'm going to replace t minus a with t prime is t minus a. Okay, so make a change of variable. And then up here, I'm going to get t prime plus a. All right. And then, dt prime. You have to mess with the limits of the integral, but it turns out that it ends up just being 0 to t back again because of periodicity. And in any case, you get, so like I said, you get t prime plus a here. And so the a pulls out of this sort of, because it's independent of t prime, pulls out front of the integral. And what you get is e to the minus 2 pi I n a over t, okay, and then it's the original CDFT. Okay, so when you shift a signal, like here, what that does to the CDFT is it multiplies it by a complex number of unit magnitude, right? So this is modulus 1. So it just changes its argument, right? So every complex number is determined by its modulus and its argument, okay? And this is modulus 1, so it just changes the argument by whatever's up there, okay? All right. All right, so now let's see if there's some very elementary properties of F which are reflected in the CDFT. Okay, so if F is even or odd, then CD is also even or odd. Okay, so that's that formula. Okay. If F is real and even, okay, or real and odd, then CDFT is real and even, or imaginary and even. Oh, right. So yes, exactly. Sorry. So F is real and odd. So the transform is I guess imaginary and odd. Sorry. Okay. So let's take a look at our examples above to see if that's verified, just for fun. Okay. So this G is even. Okay. So, right, it's if you reflected about the independent variable axis, you get the same thing back again. So it's real and even, and you can see that its CDFT is also real and even. Okay. So this function is real and odd, right? So if you extend it periodically, you're going to get something like this, which is odd. And so the transform is imaginary and also odd. Okay, so this one is odd. So here, you see the different roles played by the n and n squared in the denominator. Okay, and so this is real and even. And so this one is also real and even. Okay, so you get t squared here and sine squared, right? So both the numerator and the denominator are themselves even. Okay, and then for this one, f is again real and even, and the transform is also real and even, right? So the numerator is odd and the denominator is odd as a function of n, and so when you take the quotient, that'll be even. Okay. All right. And then a final elementary property, which is obvious, is that FCB is linear. Okay, that's just by linearity of the integral. Okay. All right. So let's now look at a slightly more interesting property of the CDFT. And this is what's called the Riemann-Lebesgue lemma. Okay. So the Riemann-Lebesgue lemma here says, so I'm going to state a version of the Riemann-Lebesgue lemma, which is a little bit very slightly more general than how we're going to make use of it here. And it says this: so if f is L1 on a compact interval AB, and if omega is some real number, then the limit as n goes to infinity with the integral from a to b, f of t e to the e to the I omega n t dt is equal to 0. Okay. And so this is different than what we're going to use it for. We're interested in t-periodic things, so we're interested in the interval 0t, not a big deal. And we're going to take the special case where omega is 2 pi over t, which isn't really the special case. It's just a renaming of the variable. Okay. All right, so that's the Riemann-Lebesgue lemma. I'm not going to give a fully comprehensive proof of the Riemann-Lebesgue lemma, but I'm going to make it hopefully believable for you. So what I'm going to do is I'm going to tell you why it's true rather than proving it. Sometimes that's a better idea. Sometimes it's not. Okay, so the way I'm going to prove the Riemann-Lebesgue lemma is I'm going to give a series of reductions of properties of the function f to a case where the lemma becomes obvious. Okay. All right, so first, so since f in in L1 AB can be approximated by g, which is a continuous function on AB, in that f minus g in the 1 norm. So when I say approximated here, that's the approximation that I'm interested in, can be made small. Okay, we can assume, and so the idea here is you're going to assume that g is continuous, and we're going to prove that this is true when g is continuous, and then we're going to use the fact that I can always find a continuous g which is close to f in the L1 norm to show that if it's true for g, it's also true for f. Okay. All right, so since that's possible, we can assume. And so in other words, it suffices to prove the result when f is continuous. Okay, so that's the first reduction. Now I'm going to make another reduction. So if f is continuous, okay, and so by the way, just to make sure we understand why this is true, why can I make this small? Given an f in L1, why can I find a continuous g so that that's true? Well, that was our whole reason for embarking on the discussion of the Lebesgue integral, was to find the completion of the continuous signals in the one norm. Okay, and that was exactly L1. And so the completion of this means precisely that given anything in here, I can find something in the thing I'm completing, which is close to it. Okay, so that's why that's true. All right, so now I am in the case where f is continuous, and if f is continuous, then there exists a step function. G with, again, G being close to f in the L1 norm. And why is that true? Well, that's true because f is continuous, so it's Riemann integrable, in fact. And so the integral that I calculated in doing the one norm is the Riemann integral. And the definition of the Riemann integral is exactly that I can approximate my functions by step functions. And approximation is precisely in the one norm. Okay. Okay, so we can assume that f is a step function. Okay, good. All right, so now if f is a step function, okay, what does that mean? So that means f is a step function, so there's a partition, a finite partition of the interval AB into subintervals. Okay, and on each subinterval, step functions are, the step function approximation will be constant. Okay, and there's a finite number of these constant subintervals in my partition, and so therefore, if I can prove a dilemma for constant functions, okay, for each one of these, then I can prove it for a finite number of them. Okay, and so therefore, without loss of generality, we can assume that f is constant. Okay, and so what I've done is by a series of reductions, I've restricted myself to the case of proving the lemma when f is a constant function. Okay, so this seems like a cheat, but really it's not. Certainly, if I'd just come out and said immediately without loss of generality, we can assume f is constant, you would have been pretty suspicious of that. But I think this chain of reasoning here is pretty convincing. It's not perfectly rigorous, I'm not saying that, but it's believable, which is sometimes even better. Okay. All right, so now we're in the situation of a constant function. Okay, so now let f from A to B be a constant function. Okay, now what does this mean? Okay, so so f is constant, so it doesn't matter, so that constant's going to come out of the integral, and really all I'm then interested in showing is that integral from A to B of the harmonic functions, as the frequency increases to infinity, that integral becomes 0. Now I claim that's obvious. Okay, so to see why the lemma is true in this case. So what I'm going to do is draw some pictures. Okay. And again, the pictures aren't rigorous, but they definitely give you the reason why the lemma is true. So A, B, okay. All right, so let's say that I have n equals 0. Okay, so that means, well, n equals 0, it's a constant function. So maybe that's not the most interesting case to look at. Let's look at the case of n equals 1. All right. And so then on the interval AB, I'm just going to have some harmonic function with frequency omega or omega over 2 pi or something. Okay. And you know, it's not going to be a harmonic function that, you know, lines up necessarily well with these endpoints. So, you know, it's not necessarily going to start at 0 and end at 0, but it doesn't really matter. Let's suppose that it looks something like this. Right. Oops. Okay. Now, as n increases, the frequency of this harmonic increases. Okay, and so I don't know what this is going to look like, but let's suppose it looks something like this. Right. Right. And then as I increase the frequency even more, okay, to, you know, very high frequencies, I'll try to give a representation of what's going on there. Okay, so we're going to get something that's you know, highly oscillatory. So it's going to maybe look like this. So that's my idea for today, of something that's highly oscillatory. Okay, so, but it's enough to illustrate the point that I want to make. Okay, and the point that I want to make is that this lobe of the harmonic function is going to cancel with this lobe. This lobe is going to cancel with this lobe, and so on. And so this one maybe comes down here. So, okay. And so the so I take that back. I'm not going to get anything there the way I've drawn it. Okay. And so the point is that the only thing that's going to contribute to the integral are going to be the little fragments at the end here. All right. And as as omega, as n becomes large, okay, the width of these little chunks at the end is going to get very small. Okay, but the magnitude is going to be bounded still by 1. Okay, and so as n gets large, the integrals of these little fragments at the end are going to get very small. Okay. And so I claim, therefore, this color argument shows that the lemma is true when f is constant. And by my chain of reductions, also true then for f is in L1. Okay. All right, so to do an official proof, you have to do more than that, but that's the idea. The rest of it is details. Okay. All right, now a corollary to this is the application to the CDFT, right? So for the CDFT, I'm going to take 0 to t, and I'm going to take omega to be 2 pi over t, okay? And then what this says is that if you have f, which is an L1 per of 0 t, then the CDFT goes to 0 as n goes to infinity. So if f is in L1 per, okay, so the CDFT of f, so it goes to 0 at infinity, but we spent some time talking about that kind of stuff. That's the space little c0. Okay. So this is nice. Okay, so before, all we were able to say is that some discrete time signal defined on the sampled, discrete frequency signal sampled on the discrete frequency domain with sampling frequency, sampling interval 1 over t. Okay. Now we know more about the CDFT, namely that it goes to 0 at infinity. Okay. So FCD then is a mapping from L1 per t to little c0. Okay, so that's nice. It makes a connection to the function spaces that we talked about previously. All right. So we talked about this one for sure and this one for sure. Okay. Now these things are normed, right? So L1 per has the one norm, right? So the one norm calculated on a period. The right norm to use for this space is the infinity norm. Okay. And you can ask, maybe the CDFT has nice properties with respect to these norms. And so to check this out, let's calculate the infinity norm of the CDFT of something. Okay. So, and the infinity norm is just calculated by, calculating the magnitude of the values. So let's calculate the magnitude of the value of the CDFT of something in L1. Okay. Right. All right, so this is a standard thing that you will have learned about integrals. All right, and as we've seen several times before, since the modulus of this is 1, this is simply and so this is the 1 norm. Okay, so what this allows us to conclude is that the infinity norm of the CDFT of f is less than or equal to the 1 norm of f. Okay, and so this means exactly, so back when we talked about continuous and bounded linear, we also talked about bilinear mappings, this means that as a mapping from this normed vector space to this normed vector space, in fact, they're both Banach spaces, but anyway, that mapping is bounded. Okay, and for normed vector spaces, boundedness is equivalent to continuity. All right. Okay. Now, so the last thing I want to talk about is we know that the CDFT is in little c0. Okay. Can you say more than that? All right. So we know that the Fourier transform, the continuous discrete Fourier transform, goes to 0 at infinity. Can you say anything at all about the rate at which it goes to 0? And the answer is no, in the following sense. Okay, so if f is in L1 per, then there exists, sorry, I take that back, I have it backwards, apologies. Okay, so given a G, which decays to 0, so on the sampled frequency domain with sampling interval 1 over t, and I'm going to take G to be some non-negative function, okay, because I'm going to be just thinking about absolute values here. Okay, and I know nothing about G except it goes to 0. Okay, so anything that goes to 0, so it can go to 0 very, very slowly. Okay. So given a G like this, there exists an F in L1 per such that the CDFT of that it decays to 0. Well, the rate isn't the same, but at least I know that it's larger than its modulus is larger than G. Okay. Right, so I have no control over the rate at which the CDFT of something in L1 goes to 0. All right, so we're going to see. Okay, so L1-ness of a signal gives me a CDFT that decays to 0. And what we're going to see is that if you pile on more properties than just L1-ness, then you can say something about the rate at which you go to 0 in frequency. All right. And so, for example, what we're going to see is that if you go with L2 instead of L1, then we get little L2 here. Okay, so little L2 means that there's a rate at which you have to go to 0 to be in little L2. All right, and we're also going to see that the rate of decay here allows you to make inferences about the character of the signal here. And so particularly what we're going to see is that the regularity of the functions in the domain of the CDFT, and by regularity, I mean continuity, differentiability, twice differentiability, and so on. The more regular the function, the more quickly it will decay here. Okay, so we're going to look at things like that and other things next time.